Hello everyone, good morning, and I welcome you all in the software verification and testing session. Today our speaker is Professor Subhajit Roy. Professor Subhajit Roy is an associate prof in IIT Kanpur. He did his PhD from IIC Bangalore. His research area includes formal methods, artificial intelligence, software engineering, programming languages, and interaction between all these areas. And by these words, I want to conclude my opening remarks, and now Subhajit sir can deliver his lectures.
Thanks, Avnish. Today we will look at. You guys have seen like how software is like not just software, but software computer systems are designed, be it hardware or software, how they are developed, how they are implemented, and also you have looked at some bit of hardware verification. So today we will look at the software side, like how do we test and verify software systems. So one thing I would mention is that please be interactive because I hate giving lectures. I generally like giving having discussions because I think there is much better learning that way. And the second is I apologize from the beginning because I'm not so well, so my voice might break. So in case you are not able to understand anything, please unmute yourself and ask me the question again. I can repeat as many times as you want. Again, there is a lot of material to cover. Again, it's not important that we cover everything, but whatever we cover, you should understand every bit of it. So that at least that is going to be my objective. Right. So let's get started. I hope the screen is visible. My slides are visible. Can you guys see my slide?
Yes, sir. Yes,
Yes,
sir.
sir.
Okay, great. Okay, um, so the first question is like, what is program testing? Just a moment. Do I have right? So program testing is about searching for inputs that could fail the program, right? So there are two things. Like we talk about program testing and we talk about program verification, and let us try to understand the difference. So when we are testing a program, our attempt is to try to fail the program in some manner. So the way we do it is that we try to excite the program with a set of inputs um, in a search that to find inputs that could reveal a bug, that could show that the program does not work as it is intended to work. On the other side of the spectrum is something called program verification. When we try to verify a program, we are trying to synthesize a mathematical proof for the correctness of the program. So we want to mathematically prove that the program works correctly no matter what is no matter what is the input. So one big thing is that if you find here, what we are trying to do is we are trying to find an a test input, right? So a test input that would show that the program does not work correctly, but here we are trying to get a mathematical proof that the program does work correctly, right? So the objective is different when we are testing or verifying. Again, when we're testing, so it's an existential question. We are trying to find, is there any input which can showcase the bug? But when we're trying to do verification, we are trying to argue about all inputs. We are trying to say that there is no input where the program would fail, right? So or the program work correctly on all inputs. So I hope this thing is clear to everybody. So let me know. Just unmute yourself and ask questions whenever if you have any questions. Any time. Okay, so now there are two important concepts, and I think you have already seen it a couple of times. Again, I think Professor Sunil also talked about these things. I think Professor Supratik also discussed something. So there are these two very important terms. One is called soundness, and one is called completeness. So given a claim C and an algorithm A that attempts to validate the claim, can somebody tell me what is soundness and what is completeness? We are completely fine with having wrong answers, uh, but let's have a discussion. No marks will get deducted.
Completeness means that the algorithm will give true always.
Algorithm will
That
give Mhm.
that or we can say that it will prove to be true or correct.
No, but there is a claim C, right? So what do you mean by true always? Like algorithm will always say the claim holds.
Yes, sir.
um but that is okay. So anybody else? But you have to somehow connect the algorithm and the claim, right? So there are cases where the claim holds and the algorithm says yes, the claim holds, the algorithm says no, the claim does not hold, the algorithm says yes, and the claim does not hold and the algorithm says no. So what exactly, which of these cases does soundness cover?
I think completeness means that the algorithm will always be able to show that if a claim is correct, it will always be able to show that the claim is correct. So that is what completeness means, I think. I mean, that is kind of what the notion is in generally, I guess.
Very
I'm
good, very
guessing.
good. Okay, okay.
Soundness means that if the algorithm says something, then it is correct.
So whenever the algorithm says that the claim holds, the claim indeed holds.
Yes.
Excellent, excellent, excellent. That is exactly what it is. So the algorithm is sound that if whenever A signals yes, that is A signals that the claim holds, the claim indeed holds, right? And completeness says that I say the algorithm A is complete if it always signals yes whenever C holds, right? So we don't miss any cases where the claim holds and the algorithm says it does not hold, right? So we are always able to handle that. And you have already seen that, like, ensuring that you have systems or algorithms which ensure soundness and completeness together is hard. But anyway, so at least we are clear with the definitions. So um, now if the claim is on the correctness of the program, so now what I want to say is that if I want to say that the program, my claim is that the program is correct, right? That is my claim C. So can you tell me, what is testing sound? Is testing complete? Is verification sound? Is verification complete? Again, I mean, I'm already saying that the claim is that the program is correct. I mean, and that there are two algorithms. There's a testing algorithm and then there is a verification algorithm. So can you tell me what does testing and like, is testing sound? Is testing complete? Is verification sound? Is verification complete? So what about testing? So can somebody argue about testing?
I
Is
think
testing? Mhm.
testing is sound, but it's not complete because it could still fail to find bad input. But verification will complete. It's complete because it will prove the entire program is correct.
Okay, I think yes, your intent is right. I mean, your understanding is right, but you have flipped it. So testing is because the claim is on the correctness of the program. So in testing, we are trying to fail the program, right? So we may not be able to. So whenever we find an input which is a violating input, whenever we find an input which fails the program, I'm sorry, we know for sure that the program is not correct, right? But if you're not able to find such an input, it doesn't mean that the program is correct, right? So soundness means that whenever the program is correct, the algorithm says yes, right? So the testing will try to find inputs, and whenever it is not able to find an input which fails the program, it will say, okay, the program looks correct. But that is not sound, right? Because maybe it just could not find that input which it was trying to find, where it would fail it. Does it sort of make sense?
Yes.
Right? And verification, on the other hand, is that it will always be sound whenever the algorithm is correct. Whenever it says yes, the algorithm is sure the program is indeed correct. But it may be the case it is not able to find a proof of correctness, right? So even if the program is correct, it may not be able to find a proof, right? For example, you guys are given a theorem to prove, and you are not able to prove it, right? So if you are not able to prove it, it does not mean that the theorem is wrong, right? It may be that you were not smart enough to find the proof, right? But if you are able to find a proof, if you could find a proof, it surely means that the theorem is correct, right? So this is what it is. So verification is sound, but testing is not sound, and uh, testing is complete, but verification is not complete. Now, be very careful, because in literature also people like say different things. Now if I say that the claim is on the presence of bugs, right? If I say that, okay, I want to see if the program has a bug, that is my claim. in that case, testing is sound, but it is not complete. Right? So it all depends on, whenever you are talking about soundness completeness, you have to be very careful of what the claim is. Right? So if your claim is on the presence of a bug, if you're saying that does the bug that I got is correct or not, then testing is sound, because whenever it found a bug, it is indeed a bug. Right? But it may not be complete because it may not be able to find like all input, may not be able to run on all inputs and find all bugs. Right? So okay, so anyway, so we will generally try to use this definition now, but I'm just having this note so that you don't get confused, like in case you're reading some literature and they have used a different claim. Okay, so now comes like how do we try to do testing, right? So there is it turns out to be the visibility of the software system that we are trying to verify. So so you can have something called black box testing or something called white box testing. So what?
Sir, I
Yeah,
have a doubt.
yeah, sure, sorry.
Sir, you made an interesting claim example by making that that let's say if I am not able to prove something wrong, that let's say a system is let's say a system of theorem I'm not able to prove, but it doesn't make but it doesn't guarantee that the theorem is wrong. Can you
Right.
provide an real life example of it? Let's say a problem that it is let's say somehow it is meant to be true, but we are not still not able to solve it or prove it.
No, so there are so many conjectures, right? So people have made so many conjectures, and there are many of these conjectures that we still do not have a proof for. So we cannot say that those conjectures are wrong, but the human race has not been smart enough to find proof for them, all of them yet. Right? So
Okay.
was that something you were looking for, or something more concrete?
Yeah, I mean that's the thing, but some kind of example, or let's say uh, in computer science or anything else.
No,
Um,
even like program verification, right? Like to say that the
mm,
program is correct is an undecidable problem, right? So if you know
okay.
this Rice's theorem, you know that it is undecidable. Like you can reduce it to halting problem, right? You can always say that whenever the program like gives the correct output, it halts, something like that. So now now the problem is that rather reduce the halting problem to it. Now the problem is that um, so now whenever you're doing verification, because you're trying to find a mathematical proof of, so now the theorem is the program is correct, right? And then with that theorem you're trying to come up with an algorithm which essentially finds a proof of correctness for that. Anyway, don't worry about it, we'll actually look at verification, and probably that will make it more clear in any case.
Okay.
So
Sure.
we'll see a very concrete not in this session, probably in the afternoon session, and maybe we can take this question again if there is something. Okay, good. So now we have this the visibility of visibility, which says that there is this notion of black box testing and white box testing, right? So what is black box testing? Black box testing means that the software system that you are trying to verify, that uh, you don't have access to the internals of that software system, right? So you do not know what is there, so you don't know the code. You are not, at least you are not looking at the code, you're not trying to reason on the code, right? You're only looking at the inputs and outputs. So you're just trying to excite the program with some inputs and trying to find out what is output it's showing. On the other hand, there are these white box testing techniques which try to actually look at the code and try to reason on the code and try to find out inputs which are like intelligently find inputs which are likely to fail the program. So whenever you're trying to come up with a testing algorithm, you have to be very careful whether you're trying to do a white box testing or a black box testing. Now there is this very interesting type of testing which is called gray box testing, which is where what you do is that you do not reason on the complete source code, but you still try to reason on something within the program, like some flow within the program. Like for example, you can profile your program and try to find out like which basic blocks are hit and which basic blocks are not hit, right? And use that information. So now you are not really looking at the source code completely, but it is, you're not only, but you're still not just restricted to use seeing only the inputs and the outputs, right? So you also have this gray box thing where you are saying that, okay, I can also make use of the profile data. So it is not as good as using the whole source code, but at the same time, it is not as bad as only looking at the input and output, right? So these tools are called like, so these are called what are called gray box testing. And if you've heard of fuzzing, so these are like, so there are these gray box fuzzers which have become very popular now, especially in the security domain. Now there are these different stages of testing. So whenever you are in industry, and you would see that there are these people do testing at various levels. So the first is what is called unit testing. So the unit testing is that you only test maybe a function or a module or a class at a time. So you're looking at testing a very small component of a system. And generally this unit testing is done by the developers. Developers try to write their modules and then unit test it and try to find out if everything is correct. The next phase of testing is what is called integration testing. So the integration testing tries to so now that developers write their own modules, they have to be integrated into the software system, and then you have to see if the whole integrated system works correctly. So integration testing looks at that. It tries to see if the whole system where all the modules are integrated works correctly. And you might have also heard of these integration nightmares where everything by its own works correctly, but when things are integrated, I mean, things start failing in very weird ways. Then there is something called system testing. So then once you have integrated your module, you would like to test the whole system and see if everything works correctly. So when you're doing integration testing, you're mainly concerned with the interfaces. You are just trying to see that when I have integrated these two components, if they work correctly together. If I integrate these two components, they start working together. So you're mostly interested in the interface between these different modules. System testing, you build the whole thing, you integrate into the whole thing, and then you try to test. And generally there is a dedicated test team which tries to do this system testing. And finally, there is something called acceptance testing. So this is generally done by the client where they try to test and say that, okay, the software system is good enough. You can deliver it back to us. So in the software engineering life cycle, you would see that development life cycle, you will see that there are these different phases that testing could be done. And for each of these tests or each of these stages, there are different tools and techniques that people use. Okay, great. Now let's start coming to the more interesting parts of like how do we test or how do we select test inputs, right? What is the algorithm that we use to test? So so there are these. So now the problem is that the set of inputs that you have, they may not even be bounded, right? Like for example, you are taking an integer as input, right? So, well, I mean, if you have integers, you may have a 32-bit integer or so on. But again, like think of strings, for example, right? So you could just have any string can be passed to your program. So it is like how do you even test, right? So you cannot keep on testing with all possible inputs. You have somehow have to try to find out a very good representative set, so that you can say that, okay, if I have tested on these inputs, I have a very good confidence that the program will work correctly on all inputs, right? So, and that is the hard part. That is the hard part, to come up with this representative set, which says that, okay, these small set of inputs sort of characterize the behavior on every other possible input, right? So, now there are these different testing strategies. The first is one of them is like what is called equivalence partitioning on inputs, right? So which, and the other is what is called structural testing based on control flow coverage. Let's look at each of them separately. So when you're looking at input partitioning, so essentially the idea is to divide your set of inputs into what are called equivalence classes, right? So the idea is, the high level intuition is that whenever you test from any input from that partition, it's as good as testing on all inputs from that partition, right? So you only need to, once you have done this partitioning, once you have divided your set of inputs in these equivalence classes, you only need to pick one element from each equivalence class, and that gives you a good confidence on things work correctly. Right? So, for example, let me just ask you a question that I mean, there may not be a single correct answer in this case. I mean, people can come up with different ways of partition, but I would like to have a small discussion. Like, for example, you are trying to test a program which adds two numbers, right? So, can you think of, so let's say it takes two numbers A and B as inputs. and it returns the sum of these numbers. Can you tell me what could be interesting equivalence classes? And these numbers are integers, let's say.
Floating point, negative numbers. When we
Let's not have floating points. Let's say we only have integers, like the inputs are parameters are always integers. So A and B are two.
You mean with negative numbers too?
Yeah, integers you can have negative numbers too, but not floats. So
Okay.
and A and B are two inputs, right? So that program accepts. So what could be good equivalence classes? No, I think you are on the right direction, Krishnan. But maybe you can you said things which were correct. So I don't know if you can slightly add to that. So what could go wrong? Like for example, what
You
could
can
go
have
wrong?
one number as positive and B as negative.
Excellent. Right. So it could be that one number is positive, one is negative. Both the numbers are negative. Both the numbers are positive. One of the numbers is zero. So these could be interesting equivalence classes, right? And now if you pick inputs from these, if you pick just one input from these classes, right? So maybe there are 6 or 7 equivalence classes. And if you pick just one number from these classes, that is sort of, in some sense, gives you a lot of confidence that the program is correct. Excellent, Christian. Thanks for the answer. So, that is how you can do input partitioning. And okay, so the other is that the other way of doing testing is doing something called control flow coverage or code coverage, right? So when you're doing code coverage, essentially what you are saying is that, can I look at the structure of the program and try to see that we are actually looking at, like, we are testing all the structural elements. Like for example, one example is what is called statement coverage. So what statement coverage says is that, or it's also called line coverage or node coverage or basic block coverage. So what statement coverage says is that, is every statement of the program hit by at least one test case? That is like, so there are some definitions. One is what is called a test case. A test case is basically an input output pair, an input which you're trying to excite the program with, and an expected output corresponding to that input, right? So that is what is called a test, right, or a test case. There is the other term is what is called a test suite. A test suite is basically a set of test cases. So you collect a set of test cases, construct a test suite. So the test suite is supposed to be representative of the behavior of the program on all possible inputs. That is what your aim is. That is what you try to achieve. So um, so so now so you say that you have 100% statement coverage if in your test suite there is at least one test case that or the other way around. So every statement in your program, or every basic block, you guys know what is a control flow graph. So in your control flow graph, every basic block in your program is hit by at least one test case in your test suite. If that happens, then you would say you have 100% statement coverage. Or the other way around. I mean, if 80% of the basic blocks are hit by collectively by the tests in your test suite, then you would say you have 80% test coverage, right? So it means that there are 20% basic blocks or lines that have not been hit by any test, right? So that is what is called statement coverage. So again, you can see that, of course, there is no theoretical guarantee here, but you can see that if you have hit almost every line in your program, right? Let's say you have a 95% or 97% line coverage, then you are like, you should be sort of confident, right? And things must have been right if you have still not got any bug yet. So the other is what is called branch coverage or decision coverage. So here what we are looking at is, we are looking at the branches in the program, right? The branches in the control program. So you are trying to say that, have you like hit both directions of every branch in your program, right? So if you have done so, then you would say you have 100% decision coverage or branch coverage. Then there is something called condition coverage. Um, so condition coverage is basically, it looks at, it's also called predicate coverage. So branch coverage looks at, like for example, if you have, let me just try to write it down. So somehow I've lost my pen tablet. I'll try to dig it out. But till then, let me reduce this. So for example, if you have like A greater than B and C less than B, right? So you could have multiple predicates in your decision, in your branch. So decision coverage looks at the whole decision at in one go, and it only tries to see if I can fail this whole thing in some way, and I can, like, if I can make this false, or I can make this, and I can make this true. So if I've been able to make this false and make this true, then you would say you have 100% decision coverage. Predicate coverage tries to say that for in a decision, it looks more closely and says that for each of the predicates in this decision, can I can I find the true and the false for every predicate in the program, in each decision in the program, right? I would try to find inputs which makes A greater than B true and false, and come up with inputs which makes C greater than D true and false, right? And collect all those set of test cases. Again, depending on how many of them you have been able to do, you will say you have that much of condition coverage. Okay, so
Sir,
yeah.
sir, which category of testing this equivalence class and control flow coverage? I mean, is it black box or white box or gray box, or is it a totally different concept?
Okay, that's a very good question. Very, very good question. Any ideas? Anybody? What do you think?
It's
I
white
think this is
box.
white box or gray box.
Right. So this is okay. So I would say that this is that's a good question. So let me think how to put it. So it is surely not black box, because you are not looking at just the inputs and the outputs. But here you're trying to come up with a test suite.
Shouldn't it be white box, because you need to check every single line in the code to make sure that you have covered that line?
Right, but then you are not looking at, you're not reasoning on the statements as such. You're only looking at the control flow graph. You're not really looking at the. So it's a little fuzzy question. So I would again, I agree with you. I would still call it white box.
In the equivalence cases, we don't checking all the program lines. So is it for white box testing?
No, we are not checking anything. So okay, so the idea is that when you're doing white box testing, so gray box is a little of a it's a little fuzzy, right? So what do you call gray box and what do you call white box, right? So generally, so now you're doing this testing, right? So you are coming up with this um, so how should I say it? So for example, so let me try to explain the main difference that people talk about when they talk about gray box and white box. So when you're saying white box, and we will see a white box testing tool very soon, we will look at what is called symbolic execution, which actually does white box testing. So what it does is, you will see that symbolic execution actually reasons on every single statement in the program, right? It tries to say that, okay, what happens if this statement executed, what happens if this statement executed, and so on. When you're doing gray box testing, what you are essentially doing is that you are you profile the program, you insert, you just say that, okay, which basically you're trying to do whatever you would do to collect these statements. You would insert this profiling information to say that, okay, which decisions are hit or which basic blocks are hit and so on, and you only consume that additional data. You don't, after that, you don't really go back and look at every line in the code, right? But here what we are saying is, I don't know if we should even classify it as white box or black box or anything like that, because here in some sense we are actually talking about constructing a test suite in some sense, right? We are just saying okay, so let me just say this way. So we are when what we are doing here is, we should not even talk about black box or white box here. What we are talking about here is, we are talking about these metrics. We are saying that, okay, so maybe I should have said this a little better. So the question is this. So let's say we have maybe two of you let's say Devdan and let's say Ashutosh, right? You guys are competing firms who are trying to come up with, who say that, okay, if you give me a software, I'll give you a good test suite for that piece of software, right? Now, let's say I want to buy your test suite. So let's say it's my software system and I want to buy these test suites for you from you. So let's say Devdan gives me his test suite, and Ashutosh gives me his test suite, and I look at them and I'm trying to find out that which of them I should buy. How to decide that whose test suite is in some sense better, right? So how do you decide? How do I say whose test suite should I buy? What do you think? I mean, so we need some sort of a metric, right? I need some sort of way of figuring it out or gauging that which test suite gives me more confidence, right? And I would buy that test suite. So here what we're doing is this, we are not even talking about generating tests, right? So when we actually talk about generating tests, then it's a question of like, is it a white box strategy of generating tests, or it is a black box strategy of generating tests, or it's a gray box strategy of generating tests, right? So that is what we mean by testing. When we talk about testing, we are talking about generating tests. Here what we're defining is only the only a metric, only a set of metrics which say that, in some sense, which qualifies a test suite and say, okay, this test suite is better than the other test suite, or this test suite is this much better than the other test suite. So we are trying to give a number or a goodness value to test suites. Does that sort of answer your question? So here we should not even talk about black box or gray box or anything like that. We're just talking about, given a test suite, how do you say which test suite is better than the other test suite? We are not saying that how do I generate this test suite. So later we will see that, like for example, if I want a test suite which has 100% statement coverage, how can I go about and build such a test suite, right? So there it's a question whether when you're generating that test suite, are you using a black box strategy? Are you only exciting the program with inputs and outputs to generate those tests, or using a white box strategy where reasoning on the statements and then trying to generate those tests? But what we are having here is only metrics. These are only coverage metrics. Have I answered the question? I mean, any doubts? Devda?
Could you
Sir,
explain
Ha.
the
Go.
difference between branch coverage and condition coverage once more?
Sure, I can explain that. But Devdan, do you think your question is answered, or should I add something?
yes, sir. It's answer quite a bit. I have to go. You have to go at least. Okay, sir. Thank you.
Okay, great. Thanks. Okay, so yeah, so let me just explain branch coverage and condition coverage one more time. Branch coverage essentially says that, like for example, if you have this if condition, right? So from here, essentially you have two branches, right? So if you have a control flow graph, you would essentially have a basic block here, and from that basic block, you would have two edges going out. So like if I hit both these edges, right? So it says that from a branch, there are two outgoing edges, right? The true edge and the false edge. So have I covered all these true and false edges in the program? If I've done that, then I would say that I have got 100% decision coverage, right? So your denominator is the number of such branch edges, and your numerator is the number of such branch edges that you have hit by some test in your test suite. When you're doing predicate coverage, then essentially what you're trying to do is you're trying to say it's not enough to even only just trying to make this whole decision true and false, right? So decision coverage looks at making this whole decision true and false, right? So if it, like, once it will try to make it true, maybe take this edge, it will try to make the whole thing false and try to take this edge. What predicate coverage does is that it actually tries to look at these internal predicates. Right? It looks more closely into these internal predicates, and it says that it is not enough to just make the whole decision true and false. I would like to make each of these conditions true and false, right? I would like to make, have I been able to get inputs which have made A greater than B true, A greater than B false, C less than D true, and C less than D false. So your denominator is all such predicates in the program, which could and two times of that, because you would like to see both the true and false values for them. And your numerator is basically you are trying to say that how many of them you have been able to hit. Does it clarify your doubt?
Yes, yes, it makes like it's clear now then.
Excellent. And then you have something called MCDC, modified condition decision coverage. Let me just skip it, but I'll just, it's slightly more but let me just point out that this is a very common strategy that is used in, like, it's a very well known coverage metric, and it is used by a lot of these space agencies and aeronautics and all that, and they trust this MCDC coverage a lot. And then there is something called path coverage. Path coverage says that let me try to cover every path in the program. So let me just, this is slightly more technical, so let me just skip it. You can read it up. It's not very difficult to understand, but let me skip it for the time being. Across these 4 strategies, do you think which of them, like in which order they exude more confidence, right? So like if I tell you that I got 100% statement coverage, does that give you more confidence? Or if I say I've got 100% branch coverage, that gives you more confidence?
Statement coverage is a subset of branch coverage. So if you
Very
cover
good.
every branch, then you will be covering every statement as well.
Very good. Very good. Very good. So now there are these questions. So does 100% statement coverage imply 100% branch coverage?
I think we have unreachable code only when there is a branching. So if we do 100% branch coverage, then we can definitely do 100% statement coverage.
No. So try to understand this. So we are not even talking about unreachable code. We are just talking about code that has not been hit, which may be reachable, but it has not been hit by any of the test suits. Any of the tests in my test suite. That is all we are saying. So whatever we have not been able to hit, it doesn't mean that it's unreachable. It is just that we have not been able to hit it. We have not been able to come up with an input which could hit that particular statement. So the question I'm asking here is that let's say I give you a test suite which has 100% statement coverage, right? Can you close your eyes and say that it also has 100% branch coverage? Can you say that?
I think yes, we can say.
Okay. Any other answers?
No, sir, it can't because let's suppose we take a as input as true, and then we cover all the statement. But it is possible that the input may be false. But we covered in the statement coverage.
Right.
In
So
branch coverage, we are covering both those.
correct.
That's why
Very good.
I
Very good.
think
Yeah.
if
So excellent, Devdan. So can somebody give me a control flow graph, a very simple control flow graph where you can show that this does not really hold? Okay, let me just, for the interest of time, let me try to do this. So like, for example, if you have, I hope this works because I don't remember, I'm just constructing things on the fly. Right. So let us say I have this particular program and I have a test input which actually takes this path. Right. I have only one test case which takes this path. So what is my statement coverage? How much is my statement coverage?
100% here.
100%. But how much is my branch coverage?
Yes, branch coverage is, you have missed one branch, so it should be less than 100%.
How much is it?
50%.
50%. Exactly.
Yeah, in this case, specifically, you have two branches, then it should be 50%.
50%. Exactly. So there are 2 branches. I could cover only one of them. So it's 50%. So though you have 100% branch coverage, it does not imply that you have 100%. Uh, uh, you have 100% statement coverage, but it does not imply that you have 100% branch coverage. Does 100% branch coverage imply 100% statement coverage?
yes, sir.
That seems to be right. Excellent. Does 100% branch coverage imply you have 100% path coverage?
No.
Right? Can somebody give me a counter example for this?
I think in the previous control flow graph, if you just duplicate it twice, then you can show that you won't cover all possible paths, the two branches, but you will cover all possible cases of the branches.
Okay, excellent. So I think that works. Let me just try that. Yeah, I really need to get my pen tablet. I don't know where I've kept it. Okay, so let us see on this particular graph. Does it work? So, okay, so there is one more basic block here. Okay, so let me see. So if you have 100% branch coverage, so what tests are you looking at? Right,
So
so
it's
excellent.
possible
Huh. So
that
now you
one,
have to, yeah, you can say, okay, so you can take one test which goes like this, one test which goes like this. So you have only do two tests and you have 100% branch coverage, right?
yes,
Right. But how much path coverage do you have?
50%.
50%. Excellent, guys. Excellent, guys. So this is, yeah, that was a very nice example. I think Yashas, thanks for it. So see, so you though you have 100% branch coverage, you still only have 50% path coverage, right? So again, path coverage exudes more confidence than branch coverage. And if you have 100% path coverage, does it mean the program has no bug? Now, this is an important question.
No, because the values within the path could be different. So you could end
Excellent.
up covering all paths, but the values could be different.
Excellent. So though I have covered all paths, every path has multiple values, and I may not have been able to hit the path with the right value that would have failed the program. Excellent. Okay, so this is sort of the essence of testing. So I have sort of, um, so like this is that sort of ABC of testing. So any questions here, I'll be happy to take, and we'll build upon this. Okay, good. So then let's go ahead. So now there are these multiple challenges that you have in program testing. The first and most important or most interesting problem is basically test generation, right? So the test generation problem is to find, in some sense, the minimum number of tests that finds the maximum number of bugs, or in some sense generates the highest coverage, right? So that's the test generation problem, or test create case or test suite synthesis problem, right? So you want to create a test suite, and you can think of it as an optimization problem, right? Of course, I mean, you can look at it a different way. You can even just think of it as a bug hunting. I don't care how many tests I'm generating, but I just want to fail the program. That is another way of looking at it. But when you're creating a test suite, then the problem is that I want the minimum number of tests which gives me the highest confidence, or which generates the highest coverage. Any question? Any can somebody say why are we talking about minimum number of tests? How does it matter how many tests? Yeah, because testing is expensive, right? And it is a pure overhead, right? You do not get a additional value by doing more testing. It has to be done, it is necessary, but again, like for example, if you have two smartphones and one smartphone has this very exciting new game that is there and few additional features, and the other smartphone that the manufacturer says, oh, I have tested this smartphone very well, so pay me more for this smartphone. You won't do that, right? I mean, you have to test it and you have to ensure that everything works correctly. So in some sense, testing does not add value to a product. It does not give you more. Like you cannot like go to the client and say, okay, pay me more because I've like got 100%. I've created test suites which are 100% coverage on this software system. People just expect things to work without any bugs. They don't give they don't care as to how you achieved it. I mean, how you achieved that confidence. So it's pure overhead, and testing is expensive because you have to have people, you have to have machines which are running those tests. So more tests means more money, and of course it adds to the cost of the product. The second is what is called test prioritization, which is, you can think of it as a ranking problem. So essentially, what you want to do is that you want to rank uh, tests. So let's say you already have a test suite, and what you want to do is that you want to rank uh, tests in such order that tests which are higher up in the rank are more likely to find bugs. Right? Why do I care about test prioritization? Why is this problem even interesting? Any ideas?
Again, testing is costly, so we need to find a test case which finds more bugs.
Yeah, but I'm still have to run the whole test suite, right? I mean, I'm not bailing out. I'm saying I'll run the whole test suite, but I just want to rank them in some order such that when I rank, like the higher guys, so I'm just ordering the test in the test suite, right? I'm just saying, let me order them in some way such that things which are higher up in the list, they are uh, likely to fail the program. So essentially, you will fail the program earlier, hopefully. So that is what it's trying to do. So why is it even useful?
Yeah, I think it is. It could be useful in mission critical, let's say part of the software system, so that let's say you make a change and you want the first system that to be tested is the critical one. So in that case, you can prioritize that test suite. If that passes, then later testing should produce.
Okay, good. So I sort of take all your answers and both of your answers. So in some sense, what you're trying to do is that, so as we said, that testing is expensive and it takes time. So it could be that your tests are running for almost a week or 10 days. It takes to run the whole test suite, right, on multiple machines, and it's not very I mean, there are cases where it can happen, right? So now the problem is that whenever you get a bug, then the developers will have to go and fix the bug. Now, if you run the whole test suite and then after like 10 days, you come back and tell them, though, these are all the bugs, fix them. For these 10 days, the developers are all sitting idle, right? Developers or maintenance engineers are all sitting idle. They are not doing anything. Instead, if you can order these tests in such a manner that the earlier tests fail the program, are more likely to fail the program, it means you'll discover the bugs earlier, right? So maybe instead of the last day, if the day two you got a bug, the developer can go back and start fixing the bug already, right? The developer doesn't have to like sit for another 8 days to like see what the bug is. So it gives you some way of sort of parallelizing activities between testing and fixing bugs. So that is why test prioritization is important, and you can understand that like why how expensive testing is. People do care about these problems. Then there is test selection. So test selection is about selecting, let's say, the top k tests which are more likely to catch errors. So this is in some sense like test case reduction. So you're saying test suite reduction. So when you're saying that you have a test suite and you want to reduce the test suite into a smaller test suite, and because maybe you do not have time to run the whole test suite, so can I select the k or some number of test suites, let's say a bounded number of test cases from the suite, which are more likely to fail the program. Then you have differential or regression testing. It says that let's say you have uh, tests which have okay, so regression testing is about, let's say you have a version of the program and let's say you have another version of the program, which is like you fix some bugs or you added some more features and got a new version of the program. Now, what you differential testing or regression testing, what it tries to do is it tries to say that has the new feature that we have added or the bugs that we have fixed, has it added some more bugs, has added bugs to the original piece of software, right? Maybe you fix something but in the process you broke something else. So regression testing is basically a set of, it's differential testing because you're trying to see that the new version that we have has not broken something, and it works correctly, the new features work correctly, and it has not like broken something which is already okay. Then there are like other problems like testing for multi-threaded and distributed systems, testing for security bugs, bug localization. So there are many other interesting problems in program testing. And of course, there is program debugging and program repair. So anyway, I'll talk about a little bit about more about debugging repair later. But let me just stop. So any questions in this segment? And if not, then the plan for today is that with this some background of program testing and program verification, the next session, or maybe now we can start now itself. So we have another half an hour. We will look at a very interesting testing strategy called symbolic execution. And then we will look at a very interesting verification strategy, which is a strategy that uses program logic called hold logic. So this is the plan for today. Again, thanks for the interaction. It was really fun to take this class. And I hope we'll keep on having this. So any questions that we want to discuss here?
So,
Yeah.
so could you again repeat the regression testing?
So regression testing is about saying that, let's say you have an existing version of the program, and let us say that you added some more features to it, right? Or there were some bugs that were reported and you fixed those bugs. So what you want to do is that you want to, so now the new software that you have has behavior which is slightly different than the earlier version. So let us say you had a software A. So after fixing these bugs or adding these features, you come up with a version which is A prime, right? So now what I want to do is, would I like to run my whole test suite? Maybe not, right? Because like running this whole test suite will take a long time. So the question is that differential testing tries to say that can I, so there are two things. One is what is called a regression test suite. Regression test suite is basically what you do is that every time you do a regression, every time you change something, you run the set of basic tests to ensure that everything that you have done so far works correctly, right? Nothing is broken. Um, Differential testing says that, okay, now I have these two versions of the program, A and A prime, they're almost similar. So can I come up with a reduced version of my test suite such that it only tries to find out inputs or where the behavior of these two programs are different, right? Where these two programs differ in their outputs, because everywhere else I don't care. Does it make sense?
Yes, sir.
So I want to select a smaller a set of tests which exposes the difference in the behavior in the versions A and A prime. Now the advantage is that it will sort of expose why is A prime different than A, right? So it might be different because you have fixed some bugs and then you have expected output should now match up, which were not matching in A. Or you might be able to see these new features which were not even present in A. So only those tests you can get through differential testing.
Okay. All right. Thank you.
I have a couple of questions.
Yes, yeah,
One,
Rajneesh, go ahead.
one is related to code coverage. So one thing I've noticed, right, like there's a couple of code coverage tools with the compilers we have today, like GCC has GCOV and LLVM has LLVM curves. So one thing is common for both of them that they don't play nice with optimizations. Like you switch on any optimization and the coverage report becomes useless. Like half of the lines are either not covered or not reported or the metrics don't work. So why does switching on like doing an optimized build of anything like impact the coverage so badly? Like
So it's not that the coverage is so the problem is that the when you're doing optimizations, it breaks the correspondence with the source code. Like that is why when you are running GDB and all that, I mean, you should also always run it with the O0 build, because when you're if you already have an optimized program, in that case it will like for example, you have already seen such things, right? You can have code motions where like one statement can move up in the program, right, or down in the program. You can have loop invariant code motion where something was in the loop but it went outside the loop. Loops can disappear. Functions can get inlined, right? Loops can get unrolled. Now because of these things, the mapping of the instructions between the source code and the target code, they don't hold anymore, right? So whenever, so so whenever you are doing coverage, generally you are looking at the source code, right? You are just saying
Yeah.
with respect to the source code, have I covered all lines? Have I covered all
Yeah.
branches and so on? But now after these optimizations, my target code, right? My target code is not even the same as my source code. The
Yeah.
control flow graph is completely different.
Yeah.
So it doesn't even make much sense of what it is like. So the correspondence is lost, right? So you would have expected that the the two branches were hit. Like for example, these two branches are hit, then I
Yeah.
would get 100% decision coverage. But in the optimized code, this basic block, it could find out that this is dead code and completely eliminate this at all, right?
Yeah. Okay. Yeah. So yeah, that branch is not. I mean, that part is not there. So
That
yeah.
part is not even there. So how do you correspond it to anything?
Yeah. Correct.
That
Understood.
is why, so the one way to do it is that you can do things at on unoptimized code, and then you just trust your compiler that optimization will not break anything. So that is one way of handling things.
So, and the second question is in fuzzing, we generate artificial test cases, right? Like, to act as input, and then you look like so. Like recently, there's been some interest in compiler fuzzing, like where you give the compiler random programs until it miscompiles or generates an error, right?
Right, right.
So, isn't the like sample space for this very large? Like the number of programs you can generate for any compiler is like infinite, right? So,
Sure.
how do you even know when to stop or when you've got into a certain threshold? Or
So one easy way of is coverage metrics. You just say that on the compiler I have covered these many paths in the compiler, or I have covered these many branches in the compiler code, and then you say, okay, it looks like I've tested enough. That is one way of doing it.
yeah, that
So
makes
you put a threshold. You said, okay, once I have hit like 170% decision coverage or 80% branch coverage, let's just stop after that. And oftentimes it is just the budget people use. Like it's generally the time budget. They say that let me run my fuzzing for 2 hours or 4 hours or 8 hours or 24 hours, and that is all I can do. I cannot run. I don't have the money. So because everything translates down to money when you are in the industry, right? So
yeah,
now you just say that I can block this machine for testing only for 24 hours. I cannot do it more than 24 hours,
yeah,
right? So then you run the program with you run the program for 24 hours, and generally these tools, these fuzzing tools and all these tools, they are primed in a way that the more uh, like parts of the code which are more likely to fail, they would try to explore first.
yeah, that makes
So like, so it means that in 24 hours, so in some sense there is diminishing returns, that if after 24 hours you have not found a bug, it is unlikely that after 48 hours you would find a bug, and still less chances that after 96 hours you would find a bug. So essentially you just run it with a time budget. And that is another, generally this is the use case people use for fuzzing. They just say that, okay, let me run it for let's say 24 hours. Let's see how many bugs we get. That is what they do. Because it's all translates to cost. It says that, okay, I have budget for holding these many machines for this much time. And let me try to run it and just see how much I can get.
yeah. I understood. Thank you.
Thanks, Ashutosh. Any other question?
Sir, sir, as we saw here, that path coverage testing covers more than branch covering, and branch covering testing covers more than statement covering. Why don't we have only use path covering? Why do we have the use of statement and branch covering testing?
Oh, that's a very good question. That's a very, very good question. Um, so the reason is that um, different people. So generally, you have a choice. Like different people in industry, like they like to um, specify the rigor of testing in different ways. Like some people might say that, okay, I really need like these much of I need a very carefully, like for example, think about it, right? There are different classes of software. There are software which are like avionic software, or software that goes into, let's say into what should I say, reactors and things like that, right? These are like very mission critical piece of softwares, and these I would like to have a very stringent testing policy and very high coverage on the testing policies. On the other hand, you can have systems which are let's say your desktop applications, or let's say your notepad or things like that. Now if they crash once in a while, I don't care so much, I'll restart it again, right? So like for these different flavors of softwares, your client might be interested in different measures, like different rigor on their testing. That is why this gives you more freedom, right? I mean, they can, it's like having different units, right? I mean, you can say, okay, I want to do things in kilograms, I also want to have grams, I also want to have pounds, right? So these are, you can think of them as different units, and you can specify things in whatever you want, whatever way you want. And like, let me just add one more thing to what you were saying. In fact, though you know that statement coverage is possibly the weakest, and possibly then there is branch coverage and predicate coverage and everything else, but even then statement coverage is many like companies, I mean, ship their product with only like statement coverage with something like even 70% or so of statement coverage, and they say that is good enough. I don't care, I cannot test anymore. So it all comes down to, so this is at the end of the day engineering, because there is no way of, like, there are no theoretical guarantees that you can give, like, by doing testing. It's just a matter of getting a bit of confidence, and having different coverage metrics gives you more confidence in specifying things. That is all that there is.
Thank you, sir. Thank you.
Okay, good. So any other question? Okay, great. So if not, then let me start with the other section, which is we'll start looking at the first very interesting testing technique called symbolic execution. Okay, great. I hope my screen is visible.
Yes, sir. Your screen is visible. Yes.
Okay, great. Thanks a lot. I don't know what happens, but it was working correctly in the previous thing, but here I've lost my participant list. Okay, this sounds good. Okay, great. Which one did I open? Hi. Uh, I came back to the same thing, is it? No, which one I have? Not close it. Okay, great. So, okay. So, so we have seen that you would like to check if a program meets the specification. So, so the aim of symbolic execution is to find an input which will fail the program, or which shows that the program does not meet the specification. So let me, I've already talked about these things. Um, so, so if I look at the testing spectrum, what we had talked about, so symbolic execution is positioned very interesting, at a very interesting space in this. So we saw that program verification is sound, again with that claim that the program is correct. With respect to that claim, program verification is sound because whenever it says the program is correct, the program is indeed correct. It is incomplete, so it means that there can be cases where the program is correct, but verifier says, well, I don't know, I can't find the proof. And program verification can talk about infinite number of inputs. It can actually reason about infinite set of inputs and say, even on these like infinite set of inputs, I can claim that the program will never fail. Program testing, on the other hand, is unsound because when even if I could not find a bug, that does not mean that the program is correct, right? I mean, it only tries to find bugs, and not being able to find a bug doesn't guarantee that the program is indeed correct. So it is unsound. Again, it is complete because whenever I find a bug, the program is indeed correct. The program is indeed faulty, and there are finite number of inputs. It can only talk about a finite number of inputs because I can only have a finite number of test cases that I have run. Symbolic execution is somewhere in the midst of verification and testing, right? So it is unsound because if you do not like, it does not guarantee that the program, like if it could not find a bug, so it's still a testing strategy, so it doesn't mean that whenever it is not able to find a bug, the program is indeed faulty. But it is what is called sound in the limit, which means that if you run it forever, sometime or the other it will find a bug. So it's sort of, I mean, it's just a weird way of saying things. It is complete like any other testing strategy. And interestingly, it can actually talk about an infinite set of inputs, unlike standard testing techniques. It can actually say that, okay, it can reason on infinite number of inputs, and we will see how. So it is, though it is classified as a program testing strategy, but it has some flavor of program verification as well. So we were talking about this closed box and open box testing strategy. So here, so the question is that whenever you have like you're same as white box and black box. So whenever you have open box or white box testing strategies, you are trying to examine the code. So in closed box strategies, you just look at the inputs and the outputs. So symbolic execution strategy, which is open box technique. So it's an open box technique. It actually, when you do symbolic execution, you have to reason on the code and try to find out what is it doing. So again, I mean, you guys have already seen control flow graphs, but again, I mean, I just had things in case you want to have a quick recap. So every node in the control flow graph is, is a basic block, and a basic block is nothing but a straight line piece of code, right? So and these are like a sequence of instruction with a single entry and a single output. So there are no jumps or jump targets within a basic block, right? It means that if you enter a basic block, you would surely you will have to run all instructions in the basic block, right? So that is what is called a basic block. And then any possible control flow from one basic block to another basic block is expressed through a control flow edge. So there are, if you can move from one basic block immediately to another basic block, then you put a control flow edge between these basic blocks. And there are always these two very important basic blocks. One is called the entry block and the other is called the exit blocks. Of course, you can have multiple exit blocks, but then I can always create these pseudo edges which go from all of these exit blocks and connect them into a single exit block. So, I'm sure all of you have already, because you have seen, you have done even optimization. So I'll not spend much time on it. You know what is a control flow graph. So this is an example of a control flow graph. I'll not talk about constructing control flow graphs. So now there is this notion of what is called a super graph. So a super graph, because I think inter-procedural analysis was not covered. So one way to do inter-procedural analysis is to construct what is called the super graph. So if for every function in your program, you can construct a control flow graph, and then you can and then you can have these and then what you can do is, whenever there is a call from one function to another function, you can actually create an edge from this control flow graph to this other control flow graph, right? So then what happens is that, and again, when there is a return, you create a return from this graph to the other graph, and I'll show you a super graph. So so doing that, what happens is that you have merged all these control flow graphs together into one big graph, and that is called a super graph. So you construct control flow graph for each function in your program, separate control flow graph for each function in your program. Whenever there is a call instruction, you create an edge from that basic block in that control flow graph to the entry basic block of the call procedure, and create another edge from the return of that procedure, the exit block of that procedure, to back to the edge which has the control flow graph, which has which had made the call. Right now, in this super graph, there could be different types of edges. There can be intra-procedural edges, that is, which are edges within the control flow graph of one function. These edges can be what are called conditional jumps, that whenever there is if some condition, go to something. So these are what are called conditional jumps. There can be fall through edges. So if condition is not hit, it goes to the next statement. That is called a fall through edge. There can be unconditional jumps. So just say go to label, right? That's called an unconditional jump. And then there is a call short circuit, which is shown by a dotted line. So you can just you can remember these colors, because I'll show you these things in the super graph. And then you have like inter-procedural edges, which go from one control flow graph to the other. And there are two edges. There is a call edge, which goes from wherever there is a call made, it goes from that call to the entry of the other basic block, to the other control flow graph, and a return edge which comes from the return back to this call. So just try to hold this for a moment, and I'll actually show you examples. Don't worry. Now let's jump to symbolic execution. Now let me ask you this question, right? I give you this program, and I ask you that, can you give me inputs which can violate this assertion? So you have this assertion which says A is greater than B. So can you find out inputs which will violate it? Or can you give me a strategy to find inputs which will violate it? So which means that you have to give me values of A, B, C, and D such that this condition is not met. Looks complicated, right? So this is what we try to do in testing. We are trying to find out inputs for A, B, C, D such that I can falsify this particular claim. I can break this assert. So any ideas if what we can do over there? Okay, it is a difficult problem. I completely agree. So let me try to see. Let me ask you a simpler question. Now this is maybe a class 8 maths question. So a customer buys 4 apples and 2 bananas for rupees 50. Another customer buys 5 apples and 4 bananas for rupees 70. Right. So what is the cost of each of these items? Can you solve this problem for me, please?
10 and 5.
Oh, you are a calculator, man. But how do you solve this? Can somebody tell you how do you solve this?
I guessed it by looking, but I think we normally would write linear equations and we'll have two simultaneous equations and we'll solve for x and y.
Excellent. So, but even I want a simpler, like a more structured answer. So, how do you write those linear equations? What would you like? How would you do that?
So the question is, what is the cost of each item? And so that is what we need to find. So there are two items, two costs which are unknown. So we
Excellent.
call them x and y, and then we apply the constant.
Very good.
4
So
plus 2.
yes. So then I say that x is the cost of an apple and y is the cost of a banana, because these are unknowns. I need to find this out. And then what I do is, then I say that 4x plus 2y is 50 and 5x plus 4y is 70. solve them, and there are LP solvers or linear solvers, which will linear equation solvers which will solve this for you. You can do it automatically through software, and you will get x and y, which are the values of these unknowns. Okay, good. So what did we do? What we did is that we had some unknowns that we wanted to find out, whose values we wanted to find out. Because we did not know those values, what we did is we just assumed that there are some variables, right? Some symbols. I represented them by some symbols, x and y. And then I created equations over these values, solve them, and you get the answer. So the big idea is that whenever there are unknowns, it makes sense to use symbols to represent those unknowns. So the simple idea to solving the testing problem is that what did you wanted to do? You wanted to find out inputs to the program which will fail the program. So the unknowns, what was unknown? The program inputs were unknown. Big idea, represent those inputs by symbols, just the way we did it for the last problem. Run the program with those symbolic inputs, right? So now instead of those inputs, you have some symbols sitting there. Run the program, run every statement that you have with those symbolic inputs. Eventually, you'll get some equations. Solve those equations. You'll find out the input which will fail the program. So again, coming back to the program that we were talking about, this is the program. So we wanted to find out the values of A, B, C, and D, which will lead to violation of this assertion. So how can we write this? How can we solve this problem? So again, because we want to find out the values of A, B, C, D, I don't know these values. These are unknowns. I represent them by symbols. So let us say the value of A is represented by the symbol alpha 0, B by alpha 1, C by alpha 2, D by alpha 3. Now what I do is I construct what is called a path condition. But anyway, I mean, that's not important. Let me not talk about this. Oh, I did not. Am I missing a slide? Acha. Oh, okay. So I take a step. Okay. So So what you do is that you represent these ABCD by these symbolic inputs: alpha 0, alpha 1, alpha 2, alpha 3. And then what you do is that you try to create an equation. How we systematically do is for later, but at least you can intuitively understand what's going on. So to reach this assert and say that A is greater than D is falsified, I know that my if condition must fail, right? So it means that whatever is the value of A, which is nothing but alpha 0, I'm just, instead of alpha, I'm writing A. So A0 less than equal to B must fail, right? So that instead of the if condition, I go to the else part, right? Only then I can, that is one way to, that is the first way of reaching the target. Then what I do is that is the first condition that must hold, and you increment D. So D's initial value was, the input that we had was alpha 3, but now the value that sits in D is D plus 1, right? So now the value sitting in D is A3 plus 1, because I have done a D equals D plus 1. Then I want this condition C to fail, right? C to succeed. Only then will I go to this, I'll reach this assertion, right? So I want this C is nothing but alpha 2, A2. A2 is equal to 2 times D, but then D has a modified value now, which is alpha 3 plus 1. So A3 plus 1. So this must hold. Now I've reached the assertion. Now what I want to do is I want to ensure that this assertion fails. I don't want this assertion to succeed. So what do I do now? I must have a value where A greater than D becomes false. So what is A? A is alpha 0, A 0. Greater than D, D has a modified value which is A3 plus 1. And I want this to fail. I don't want this to succeed. So not of this. Good. So what I have been able to do is, using these symbolic values, we have been able to construct a condition. This is called a path condition because you see that it actually takes a path in the program, right? If you anything that satisfies this particular equation will exactly take that path in the program. Now once you have this particular condition, in fact, I mean, you don't put the assertion until the first two terms as the path condition, because it will always reach the assert. Anything that satisfies the first two terms together will always reach this assert. And the last condition is for the assert to fail. Now you know there are these SAT solvers and SMT solvers that you guys had already learned about. They can solve things in like propositional logic or first order logic. Now this is something in assuming ABC are integers and so on. So this is a first order logic fragment. Now you just give it to one of these SMT solvers. They will solve for these unknowns, which is this A0, A2, A3, A1, and so on. And here you get the inputs that will actually violate this program, violate this assertion in the program, right? So it's as simple as solving your eighth class mathematical problems that you were solving. There is one big idea. Whenever there are unknowns, replace them by symbols. Construct the path which leads to the violation. You get a path condition. Add the negation of the assertion that you're trying to fill there. Solve for it, and it will give you the values which will surely fail. Of course, there can be multiple values which will fail this. You will get one of these satisfied assignments. One such value which will fail it. Right? And if you want more, you can always ask it for more values. Right? Any questions with this idea, the basic idea? How we systematically do it, we will figure it out. But at least do we understand the basic idea how symbolic execution works? It's a very simple idea, nothing very complicated.